Okay, so welcome everyone. This is lecture 4. So let me get started with some logistics and then we'll get to the details of today's lecture. So first thing, assignment 1, so deadline was yesterday. So I hope all teams were formed and they were informed. So the TA was informed about the teams and each team submitted one submission. So if there are any questions about the assignment, you can ask now. In the meantime, assignment 2 is the deadline is September 30th, I think, end of this month. So was everybody okay with most of the questions in assignment 2, sorry, assignment 1? I guess no response means everybody's good. Okay. Okay, so it might have seemed laborious, but from next assignment onwards, we're going to use packages predominantly, and you did use Keras and TensorFlow last time. We're going to potentially use many of the predefined classes and objects in PyTorch, for example. Okay, so that's good. Next, I just wanted to briefly go over the course webpage. Okay, so the course webpage or the course content webpage has been slightly updated. I guess the most important thing is I've added lecture goals. So let me quickly recap what were the goals from before, although I mentioned it verbally in those lectures. So, and it gives you a mini recap of where we are headed and what we've done so far. So in lecture 1, the goals were to understand the key components of a classification task. So we talked about data, models, optimization, and then we spent and then we looked at, we spent a little bit of time on understanding how to map business problems to ML methods and how important it is to think about the business problem first. And the technique itself is actually 5% of the whole job. So 95% is actually to define the problem really well and have the supporting infrastructure to be able to use machine learning effectively. And then the technical part of the first lecture involved looking at backpropagation or chain rule, and we worked out a few examples in the class, and it was also there in your assignment. And then we also, towards the end, looked at multi-class logistic regression. It's basically an instance of a neural network without any hidden layers. And we saw that it doesn't work well for a specific synthetic data that we generated. So those were the goals to understand these 4 ideas. In lecture 2, we briefly went over and did a recap of essential data structures in Python, abstract data types in Python, essentially a list and a dictionary, for example. And we also tried out some details on NumPy. Then we looked at the notion of nonlinearities or activation functions, sigmoid, ReLU, tanh, and so on. And then we first, defined what is for example, a 2-layer neural network, 2-layer feedforward neural network. It will have one hidden layer. And so we, the layer was hidden basically because it was an intermediate computation and you don't really expose the outputs. If you think of a model as an object, with an API contract. Then we looked at what were convolutional layers and pooling layers. So those were 2 additional layers we introduced after looking at a feedforward network. So convolution layer, you can just think of it as a collection of filters that each filter just produces one output splice. And so we had this tensor view of this layer-wise operation. Filters kind of help us reduce the dimensionality of our model in terms of the number of parameters, as well as exploit some spatial aspects that are, that we assume is going to be there in, for example, image type of data. And then we looked at pooling as a way to reduce dimensionality, of the tensor, so that you can deal with lesser number of parameters towards, in the next layer and so on. Okay. In lecture 3, we spent a little bit more time on CNNs. In this case, assuming that we had a trained CNN, we wanted to understand how to see whether the CNN is working effectively or not. And so the first part was mostly about debugging essentially a CNN, or in fact the same ideas can be used for any neural network or any other model actually. And then we looked at how to transfer parameters from a previously learned task previously learned model to a new task. And so towards the end of this last lecture, I briefly showed you the use of ResNet 18 to do a classification of bees versus ants. So, and it showed both types of fine tuning, just feature extraction, as well as both types of transfer learning. One, just as using a pre-trained network as a feature extractor, as well as fine-tuning some of the layers in the pre-trained network as well. And then the third part that was the goal of the last lecture was to understand various additional techniques, such as a dropout as a regularization technique and batch normalization as a way to stabilize the training of the network. And we also looked at one more technique, not specific to models, but to actually image type data, which is called data augmentation. And it really was exploiting the the idea that images, if they're slightly cropped or slightly perturbed or slightly rotated, you should have the same label. Let's say if you're doing classification. So those are the goals for the first 3 lectures, and there were corresponding notebooks and links available for each. So with that, let me go over to today's objective. So today we're going to switch gears and go away from images to textual data. And so the topic for today is Introduction to Natural Language Processing and the idea of word embeddings, in particular the Word2Vec embedding, which is a classical idea in this class of topics. So what are the goals? First goal is to understand how natural language elements are processed in an analytics workflow. So you don't have to use deep learning techniques here. There are some previously established methods to work with textual data. So we'll try to look at that. And then we'll try to look at some of the shortcomings in these methods. And in particular, we're going to look at a couple of methods, including naive-Bayes and what is called latent digital allocation. So I'll tell you what the objective is and what does the method or the model assume, and how do you use it. Next, we'll also see that a CNN can be used to do a task with text data. In fact, you can use a CNN for sentence classification. So it should be a good example there. And then we'll move on to the main object of today's lecture, which is word embeddings. And we'll see how word embeddings, in particular Word2Vec, which is an instance of that, can help us in this natural language processing task. So that's the lay of the land. Okay. If you have any questions about any of this so far, use the chat feature. Okay. Yeah. So can everybody see my screen? So this is I'm instead of using I guess OneDrive, I'm using OneNote. You can actually see previous lectures, annotated lectures on this class notebook. So everybody has access to it, and you have your own space where you can write down something and share it with the teaching staff, me, or the TA. Okay. So it's quite useful. Try to use it in addition to other sources, other channels of communication. So let's start. So I just wanted to quickly give a teaser on, on a vision problem. So this is so CVPR is actually a conference for vision related machine learning research. So in 2017, one of the best papers was a paper called Densely Connected Convolutional Networks. Okay, so many of the things that we're seeing in this course are relatively new. If not last month, they're probably 5 years old or maximum 10 years old. So this paper, I wanted to highlight this paper because it's a idea which is on the face of it quite straightforward. So if you remember AlexNet or even VGG 16 or 19, they had this layered architecture where there would be a few convolutional layers, and then they would produce some output tensors. And those output tensors will be passed on to the subsequent layers, which could be a fully connected layer, a pooling layer, or a subsequent convolution layer. So the idea in this paper was to not just do a sequential passing of these tensors. So if I have a tensor T1, maybe after some layer processing, after layer it became tensor 2, T2, and then became tensor T3, and so on. Right? At the end of the day, it will become a, let's say if we are looking at classification, it will become a score vector, which is a tensor with height and width, height and width being 1, and depth being the number of classes. Okay. So the idea here is to actually connect these. So there's a layer here, these vertical lines, let's say. So the second layer, so let's say this is the second layer, it's not only getting tensor T2, but it will also get tensor T1. So that was the key idea here. So the layer which is going to take tensor T3 as an input is not only going to process tensor T3, but also process tensor T2 and also tensor T1. Okay, so you can see that being illustrated in this figure here, and so what is the I guess the idea behind it is that there may be information. So certainly tensor T3 is some processed version of tensor T2, which is a processed version of tensor T1, but there could be still some information that might not have been fully captured in T2 for the ultimate task, which is, let's say, classification. And you can fix that by really passing the all the previous tensors to the next node. Okay, so that's the key idea. And of course, when I say, let's say, in addition to T3, I pass the previous two tensors, you need to somehow collect them together into a bigger tensor, for example, or even if you don't see it as a bigger tensor, somehow you need to figure out how the layer is going to process three tensors at the same time to produce one tensor at the output. Okay? So model of that, detail. This was the idea, and they showed a really good performance on a variety of tasks, I think. So just to give you an example of what type of simple architectures, but with some heuristic or some at least intuitive reasoning of why something may work, goes a long way. Okay, so let me now switch to our objective. As I said, we'll have kind of three parts to this lecture. First, we'll look at the basics of NLP, and then move on to some simpler methods, which include, as I said, naive Bayes and latent initial allocation, for instance. And next, I will, and towards the end, we'll talk about word embedding. So there's a question about assignment. Am I seeing it's late or maybe not? Okay, so there was a question about assignment. I missed it, so let me just quickly take that before I jump into NLP. Generally, do we stick to a particular optimizer like Adam, or is it specific to the kind of problem in hand? So there's actually there's two parts of the answer, at least. So there are well-known classes of optimization problems for which, and for each class, there is probably a best family of optimization techniques. Okay. So for example, when I say classes of optimization problems, think of continuous optimization has a class of problems called convex optimization problems. Okay, convex optimization problems, the loss function or the objective function is somewhat nice, and for that there are not just methods like Adam. There are methods like you know, second order methods that so gradient descent methods are called first order methods, but there are other methods like second order methods which take into account the gradient of the gradient, essentially the Hessian, to inform how to make progress from the first candidate parameters to the next candidate parameters and so on. So for some classes of problems, we know what is the best class of techniques or a technique to solve the problem best in terms of the number of iterations to get to a really good answer, or high quality answer. The error with the same number of iterations. Like, let's say if you compare two algorithms, two optimization techniques, for the same number of iterations, maybe one gets much closer to the optimal solution, as in the best loss type of a solution and so on. Okay. But it turns out for neural networks, it's the optimization problem is really messy, and that is why we were talking about weight initialization last time in the last lecture. And so it's still a continuous optimization problem, but because of at least the models that we have seen, and for them, it is really unclear what is the right first order technique. First order means techniques which use gradient information about the loss function. So Adam is one. You can default use Adam, and it seems to work fine. The idea of momentum and so on seems to work fine for a large class of problems. But there are other techniques that you might have investigated already. The vanilla SGD, there's something called RMS prop, and so on. So all these are in the same family, but have different ways to go from a current candidate of parameters to the next kind of candidate parameters. We will look at optimization techniques at a later lecture and revisit these notions, the different techniques, for example. Maybe we'll have a longer discussion there. But for now, you can just think of using Adam as a technique in your collection of techniques to optimize a neural network. But the best optimizer definitely depends on the problem at hand. You would not want to use, there's a matching between the right optimizers to use for the right problem. Okay. And I was talking about continuous optimization problems just to give a sense. There are also discrete optimization problems, which is where, which is something that you might see in another course like supply chain optimization, supply chain and planning problems, or even revenue management problems where you need to take, for example, let's say decisions, maybe even in healthcare operations where you need to take decisions like the number of beds or the staffing of personnel in different departments. So they tend to be more discrete in nature. So I can only have 5 people or 6 people as a solution to the staffing problem. And so those are integer or combinatorial optimization problems. And for them, there is going to be a different class of techniques. Okay. So let's first talk about a little bit about natural language processing. So some of you have seen natural language processing in potentially 572 or maybe in some other course. So natural language processing is all about trying to work with natural languages. Natural languages are languages like English or any of the thousands of languages in the world. What we'll do today is look at a very narrow set of topics in this area. And I guess from our perspective, essentially, text is going to be just a sequence of symbols. Okay, and we can ascribe numbers to it, and that's what we'll do essentially in this lecture. But in the raw form, it's a sequence of symbols, letters, or alphabets, or a sequence of words, for example. And there are several ways to represent it. One way is to one-hot encode them as vectors, right? So each symbol gets a number. It doesn't even have to be one-hot encoded. Each symbol I can just assign an arbitrary integer, for example. And that's one representation of text into something which is essentially numbers. And we care about numbers because computations really work on computers, and computation really is on numbers, right? And the more interesting, a little bit more interesting way is to one-hot encode your vectors. It just means that if I have 3 words, word 1, word 2, and word 3, word 1 would be, let's say this is my vocabulary. then Word1 would be using a three-dimensional vector 1, 0, 0. Word2 could be a three-dimensional vector like this, 0, 1, 0, and third vector could be 0, 0, 1. Okay. That's what one-hot encoding means. Let me motivate the business problems, or at least some practical problems first. The first one is machine translation, and you can imagine how useful it is, given that there are so many different nations and cultures and languages. So a translation, a computer-based translation solution could be immensely useful. And so the input in this case could be an English sentence, and an output could be, for example, in Spanish. And a very prominent example of a free to use for individuals translation service is Google Translate. Right. So you can imagine that what is the computation behind such a solution, and you'll see that some of the solution ideas to do this, to get to a solution such as Google Translate, will involve not just neural networks but a really good representation of languages. The second example is query answering. So at least this is the goal of a good chunk of research these days, which is to produce, given a document as an input and a query as an input, the computer or a solution has to give the answer to the query. Okay, and the answer to the query will, of course, be a part of the document, but to compress, somehow represent the document in a way such that it is, a machine is able to answer the query, really requires some novel ideas in terms of representing text again. The next example is speech-to-speech translation. Sorry, speech-to-speech translation. So you're going from English speech to, let's say, Spanish speech. Then we know how to do this. This is machine translation, and we just saw an example. I mean, we saw there are services which do this. But you can imagine going from this speech signal to the language, to these language symbols, sequence of language symbols, and then going from this sequence to a completely, to again a speech representation. Okay, so this is again yet another example, and there's a lot of work in the three components, and we just mentioned machine translation, but there's also a very active area of research called speech recognition with various sub-problems there and various solutions over the past few decades. And there is the third component is text-to-speech, and this is also an active area of research with several solutions. Next is a harder problem than the textual query answering example that we saw earlier. Here, it's a visual question answering problem where the input is an image and a query, and the machine is supposed to produce an answer. Okay, and so you can imagine here there's multimodality by which I mean that there's two types of unstructured data being worked on here. One is trying to understand what the query even means, and that really requires understanding text or natural language to some level by a machine. And the second, I guess, mode is visual, right? Image-based images, and we saw some examples of how to work with images last time. So that's another example. And finally, the last example is not really an example of a particular problem, but the complexities involved in working with languages. So there are three sets of examples here. The first example is that of sense. So if you look at the sentence, I saw her duck, and we're going to look at English. I saw her duck, whether it is someone's duck that this person saw, or whether they saw some person, duck as in go underneath something, or kneel to the ground. So how can a machine infer that, right? So there is some sort of a difficulty here, and of course, if there's context, there's surrounding sentences which describe the scene or the situation, maybe you can infer it properly. Next is the idioms. Idioms are an interesting component of many languages, including English. So idioms just mean he kicked the bucket actually means something different from the literal translation of that, literal understanding of that sentence. So he kicked the bucket means they passed away, right? Whereas that is difficult for a machine to, you know, use in that sense unless it understands idioms and their occurrence when they suddenly occur, for example. So this is another challenge. And finally, the challenge of reference, which is, for example, look at this sentence: the ball does not fit in the box because it was too big or small. Okay, so now what does does it mean? So does it mean the ball or does it mean the box? Okay, you can try to, I mean, so this is something that we can potentially understand depending on context, but again, it's a little bit hard for computers or an automated solution or a machine learning based solution to really deal with. Okay, these are some examples of things that really are hard for machines to deal with, but hopefully they can be progressed in that direction. Okay, so that's a very brief intro to NLP. There are many tasks in NLP, so that's a full course in itself, with appropriate data pre-processing, data representation, and modeling, and so on. But we'll look at a few sample representations, which will get us to understand the notion of word embeddings, which is the main, which is the main part of this lecture. So let's start with simple representation. So simple models, essentially. So in these simple models, what we'll see is we're going to sidestep word-to-word relationships, in the sense that we're not really going to look at a relationship between a word one and a word two. So one-hot encoding is an example of this. That representation here. If you just look at these word, this one-hot one-encoded representations, I'm talking about these vectors as representations. And in fact, these vectors can also be called embeddings, just as a teaser. So you can see that if I look at these two vectors, they, first of all, they're not linearly dependent. If you look at some sort of a distance between these two vectors, you can see that the distance between these two vectors is, that's a square root 2, if you look at the L2 distance. But the distance between word 2 and word 3 is also square root 2. So it's not, so distance-wise, all these vectors, all these words are equidistant from each other in terms of an L2 distance on these one-hot representations. And so it's, you're really not, there is no relationship essentially between, and they're all linearly independent of each other in terms of, in terms of linear algebra. So there is no word-to-word relationship captured here in this representation. Okay. So what I'm trying to say is that the first few techniques that we'll see, they're not really specific to. They're not really looking at even word one being a dog and the word two being, let's say, cat, and word three being a house. Dog and cat maybe are categories, fall under the animal category, so they may have some closer relationship compared to a house or something. So that's not going to be explicitly captured. Okay. So let's look at a few examples first, a few concrete models and tasks and models. So we're going to look at a naive-Bayes model, and this is just a recap. Many of you must have seen naive-Bayes models before. And we'll look at, this is a classification task, which is essentially the specific task is going to be spam filtering. The next example is a building of what is called a language model. And then the here motivation is to understand what is a language model. The task is to, if you can model language, you can compute all sorts of conditional probabilities that can be useful for machine translation or generating machine-generated, sentences and so on. The third task and third model corresponding to that task. The third task is just to cluster a bunch of documents. There are no labels here. And so the technique or the model is called latent digital allocation. So here the task is just to do a cluster to make sense of a bunch of documents, okay? Like SEC filings or news articles or whatever. You can also do, clustering of tweets, for example. The next technique is a conditional random fields, and it's for classification. I think I've moved it to appendix. If time permits, we're going to visit that. And the last one, before we jump on to word embeddings, is going to be a CNN-based sentence classification. So the task is only classification task, but we're going to use a CNN, and we'll see how a CNN can be used for textual data in that part. Okay. So these are some examples and examples that work with words or natural language. Okay, let's start with naive-based spam filters. Any questions up to this point of where we're going in this section of the lecture? Okay, so just to let's start with naive base. So what is the objective? The objective is to let me just try it here. I don't know if you guys can see. Yeah, okay. I mean, if it's not visible, then let me know. I can change it. There's a huge contrast between white and the dark background here. So spam classification, right? So I have a let's say a bunch of emails, spam and not spam. It are the labels. So email 1 is going to be a bunch of text, right? Some text, and similarly email 2 is a bunch of text with the head, with the salutation, with the ending, and so on, right? So our data set is essentially a bunch of such emails and their labels. Okay, so given emails and labels as the training data, we want to build a model which will, given a new email, give me two numbers. What is the probability that's a spam, and what's the probability that it's not spam? Of course, they have to sum to 1 because of the only two choices that I'm allowing the model to make. Okay, so the model has to produce two numbers. Now, what the model is going to assume in this particular example, the model is going to start with a slightly different question, which is the following. It's going to say, what is the probability of seeing a bunch of words given that it's spam? Okay. So for simplicity, I'm going to assume that my vocabulary is of size n. So the number of words that I have is of size n, which say some 50,000. Okay. And why is it a fixed number? You can, even if you have more words, you can drop the words that are not there in your vocabulary, for example, right? If you're thinking of English. So I'm going to say there are 50,000 words. If the email was actually spam, what is the probability of me observing word 1, word 2, word 3, word 4, and word n? Okay, these are all the words. And naive Bayes is going to assume that this conditional probability is actually equal to a product of a bunch of conditional probabilities. So it's going to assume conditional independence. Okay, conditional independence. So the words are conditionally independent given the label spam. Okay, so and so this is the key assumption. That's why I guess that gives its name naive Bayes. And so it'll start with this slightly different question, and if so assuming this, then it can find the probability of a spam given any sequence of words. So what are these W1 to Wn? So by the way, in this notation, the arguments should all be random variables. Change the shade. So let me stick to the white area. I think here you can see. Let me stick to the white area first, and when I go to that area, I'll change the color. Okay. So firstly, you should notice that these guys, W1, Wn, and spam, they're all random variables. Okay. So and so that's why this is the conditional probability. So we make this assumption, and then we come back to our question, which is that what is the probability of the random variable spam being equal to 1? Let's say the random variable spam is equal to 1 means it's a spam, is equal to 0 means it's not spam, given that these words occur. So given these random variables realize some values. Okay. Now, since I said the vocabulary size is n, these random variables should be indicators of the words. Okay. So basically, if word 1 is present in the email, then W1 is equal to 1. If word1 is not present in the email, then word1 is equal to 0. Okay, so remember we have vocabulary size 50,000. So I have all these words. In a particular email, only some of the words will be present and some will not be present. I'm just saying that the ones which are present, for those, the random variables will be equal to 1. Okay, so we want to answer this question. Given a particular email, which means that some of these random variables are 1 for that email, what is the probability that it is equal, is spam? Okay, which means that what is the probability that spam is equal to 1? Let's say spam is a binary random variable. So all these random variables in this equation here are binary. Okay. Now we know from Bayes' rule, this conditional probability can be decomposed in this way. So we are not going to write the denominator, but so this symbol here is a proportionality symbol. We're just going to look at the numerator here and use Bayes' rule. So the numerator is just going to be the joint probability of all the words and spam. Okay, so let me see. So can you see red better? So probability of spam. Okay, you can see the red better. Okay, probability of spam, comma, word1, word2, and all the way to word. So this is a joint distribution of all these random variables. Okay, this is and by assumption, we know the probability of this joint distribution is the probability of spam. I mean, this is not assumption. Probability of spam, probability of W1, all the way to Wn given spam. Okay, this is just a by definition law of conditional. Is just a definition of conditional probability. And this by this here we assume something. So probability of spam times the probability product over I is equal to 1 to n of probability of Wi given spam. And so that's what's written here. That's what's written here. And the proportionality sign is because, remember, a conditional probability, which is on the left-hand side, is equal to the joint distribution divided by some marginal. Okay, the marginal in the denominator is just going to be the marginal probability of all the words occurring. Okay, but we don't care about that. So, okay, the bottom line is that if you want to classify a new text, a new email is going to be spam or not, we'll have to compute the right-hand side. Okay, for two things. We have to compute the right-hand side to figure out, by assuming that it is probably a spam, what is the score? That's the right-hand side. I will evaluate to some number. When spam is 0, then which means that it's not spam, the right-hand side will give another number. So you can compare those two numbers, and whichever number is higher, you're going to call that as the label for that email. Okay. So I guess it will become clearer once I'm going to spend a couple of more slides on this, repeating the same idea. And I talk about parameter estimation here, but let me talk about it right after the next slide. So let's come back to the assumption again. So the assumption can be actually represented using a graph. Okay, so this is called a graphical model. I mean, a naive-Bayes model is an example of a graphical model. Okay, which just means that there is a graph associated with the joint distribution between the random variables. Remember, spam is a random variable, W1 is a random variable, all these guys are random variables. Okay, I mean all the words in my vocabulary, the indicator variables related to those words are random variables. Okay, so these are all random variables, and so there's a joint distribution between them, between spam and all these guys, which I just wrote in the which I just wrote here. This is a joint distribution, and because I said it's an example of a graphical model, we can actually represent this bunch of random variables as nodes with some edges connected to it. Okay, so in particular, I'm going to put the spam random variable at the top and all the words at the, as circles or nodes of a graph with the words at the bottom. And I'll draw a directed edge from spam to W1, directed edge from spam to W2, and so on. Okay, these directed edges mean give an interpretation of how a spam email gets generated or how a non-spam email gets generated. Okay, and the interpretation is this way. So because it's a directed edge, you can start from the spam node because there is no incoming edge to that. You flip a coin. Remember, spam is a binary variable. It either evaluates to 1 or 0. Or let's say if it's 1, it's spam. So you flip that random variable, as in you flip a coin. Okay, And if the coin lands heads, or you flip a coin and lands heads, so let's say heads is 1, then it is a spam. Then you realize this random variable. So it was a, it said it is spam. So then what you do is you try to find all the subsequent, evaluate the values of the subsequent nodes in this graph. Okay, because there's a directed edge, since you already have a value of spam, let's say is equal to 1, therefore it's spam, you can find the value of W1. And why can I do that? Because I have these conditional probabilities. Once I have a joint distribution between a bunch of random variables, I can compute any conditional probability. In particular, I'm going to look at these conditional probabilities, probabilities of Wi given spam, or W1 given spam. Okay? So there'll be some number. Again, as I said, these are binary random variables, so they either take a value 1 or 0. And so if they're binary random variables, it's essentially a Bernoulli random variable with some bias. Okay, so the bias is what, so given that we want to generate a spam email, there'll be some bias towards bias in terms of the parameter of the Bernoulli for the realization of word 1. Let's say word 1 is something like buy, buy. Maybe it's not a spam, but buy something. Okay, so buy is the word, B-U-Y. Then maybe the probability that the buy word appears is higher. So think of that random variable W1 representing whether the buy word appears or not. Then the probability with which it appears is higher, maybe when the spam is true. And the probability with which it appears is smaller when spam is not true. Okay, so that's what this graphical notation means. And on the right-hand side is a more compact way to show the same graph. So one node here, and because the second node, instead of copying the second node again and again, they just put a, what is called, put a box and say that the variable repeats, n times, and what is the generic variable there, which is Wi. Okay, so the left and right side are the same thing. It's just a graphical representation of a joint distribution. And Naibase is an example of a model which is a generative model. Okay, I think some of you might have seen a generative model versus a discriminative model. Okay. And why the name generative model? Because you can generate an example, which is, once we evaluate spam, and if spam is equal to 1, then we can generate a particular email, particular email, which is just a collection of words in our representation, if spam is true. Okay, so we can generate a particular example of example instance when spam is true. Okay, so here, these are all words. These are all dashes here. Another thing you will notice, which I did not explicitly point out, is that there is no order relationship that we're capturing using this model. Okay, you can see that here directly. Probability of spam, given this bunch of words, whether I write W1 first or W2 first doesn't matter. And you can see that here, for example, even after the assumption, the probability of this collection of words is just just breaks down into the probability of individual words given spam. But there is no, whether the word 1 appears first in the email or word 1 appears at the end of the email, it doesn't matter in this model. Okay. Okay, so now let me talk about, okay, let me call this not spam. And then let me talk about estimation now. So this is a model, it will have parameters. And what are the parameters? The parameters, as I said, if you go back here again, we want to compute two numbers. Okay, we have the words, right? We have the words. So at test time, we have a bunch of words, W1, W2, all the way to Wn. At test time, maybe some words are there in the test email and some words are not there. So given that, we want to compute two things. We want to compute also the probability of spam is equal to 1 given this words, and what is the probability of spam is equal to 0 will be just the 1 minus this number. Right? Now to do that, we just use a Bayes assumption, and we got that this is proportional to probability of spam is equal to 1 times a product of the probability of Wi given spam, right? Okay, so I'm multiplying n numbers here and then one number here. Now, which means that for me to classify for a given test instance, can you shade off the marker? Okay. Is that better? I think this is asked 10 minutes ago. I apologize, but oh no, it was the same question. Okay. Yeah, so now for a given test instance, W1 to W1 being some email, I want to find whether it's spam or not. If probability of spam is equal to 1 is greater than probability of spam is equal to 0, then I'll classify it as spam, right? To get that number, I need to compute this product, okay? To compute this product, I need these numbers, okay? Every number here is what I need. And these are the I can get from training data. So if I have my training data, then I can compute what's the probability of spam is equal to 1, true, and what's the probability of each word being true given spam. Okay, and that's what's captured here. So what you do is count the occurrences of features for spam and ham. Ham, just think of it as not spam. Occurrence of feature. Feature is just the WIs, right? So feature is whether the word is present or not. So yeah, so the occurrence of a word is present or not. Let's say here I'm using x's, but it should be w's. So x is equal to w here, xi is equal to wi. So the probability of word is equal to present, given that it's spam or not, is just a joint occurrence. In the training data, look at all the rows which correspond to spam, and in those rows, look at whether the word was there in the input variable in the input vector. Okay, count the number of such rows, divide by the number of rows in which you actually had spam. Okay, so this is just counting and normalizing, and with that you will get the estimate for this, guys, for words given spam. Okay, similarly, what is the estimate for probability of spam? If you have 100 examples in your training data, then maybe 30 of them were spam, labeled spam, and 60, remaining 70 were not spam, then the probability of spam is equal to 1 is just 30 by 100. Okay, this is just a very simple estimate. You just look at the outcome variable in your training data and what's the proportion of times it was equal to spam. Okay, so it's 30 rows out of 100 rows. So then this estimate probability of spam is equal to 0.3. Okay, so with that you can estimate this whole probability of spam is equal to 1 given the. So I think some of you already know this. So I'm just recapping how you would define the model, what's the assumption, and how would you estimate the parameters of the model. Okay, so any questions about naive Bayes? If I'm going to move on to another task and another model example.
So you said it's a generative model. Why is it generative?
So you must have seen, I don't know if you've seen generative models versus discriminative models before. Generative models just mean you have the base object is essentially a joint distribution between x and y. Okay, so let's say x is the input variable, maybe it's a vector, and y is a label, or it could be a real number as well. So in generative models, there is a starting point is always a starting point is always a joint distribution between both the input and output variables. Okay, so naive Bayes, and I don't know if you guys have seen linear discriminant analysis.
Oh yeah. Yep.
They are generative models. Okay, there's actually a joint distribution between x and y. Or if you don't specify the joint distribution, you should specify, for example, probability of x given y and probability of y, or with which if you multiply both of them, you'll get the joint distribution. Or you specify probability of y given x, and you specify probability of x as well. Okay, either these two, or you directly specify this. As opposed to in discriminative models, you only are concerned with probability of y given x. Okay, you don't really care. So this is not really a specification of a full joint distribution between x and y, right? Because if I just tell me this, I don't know what the joint distribution between x and y is. Okay,
Yep.
so generative models include logistic regression, where literally you specify this, and many of the other models like SVM and so on. I mean, although SVM is not exactly going to spit out probabilities, but most models, if they say they're predicting classes, so most multi-class classifiers. In fact, most of the classifiers you'll see, like the feedforward networks or the networks that you trained in an assignment, they are essentially producing a bunch of score vectors, and then on which, if you do a softmax transformation, they're essentially probabilities, right? 0.1, 0.3, and then let's say 0.6. Okay, so that these probabilities sum up to 1, right? So these are producing probabilities, these multi-class classifiers. So, but their starting point is X, and they're saying, oh, this is the probability of outcome variable being, first class, second class, or third class. But you don't know what the distribution of X is, and you don't really concern yourself with that at all. So those would be examples of discriminative classifiers, discriminative models.
Cool. Yep. Thank you.
So next example of a slightly different task, aren't linear models discriminative? So it's logistic generative. Linear models discriminate. So no, I think the generative and discriminative distinction is mostly about whether you specify the full joint distribution between the random variables of interest, in particular the input and output variables, or not. Whether the relationship between X and Y is considered linear or not. So for example, in linear regression, sorry. So in linear regression, you assume that the conditional expectation of Y given X is linear. Okay, it's some beta transpose X or something. But this is, so here, of course, X and Y are random variables. Okay, and because I'm conditioning on Y, I'm not even saying much about X. So if I said this is true, and I also tell you what is P of X, okay, then it's a generative model. So generally in these models, you only say that Y is equal to, let's say, beta transpose X. You start with the assumption that Y is equal to beta transpose X plus C, or epsilon, sorry, where epsilon is a normal distribution. Okay. If I don't tell you anything about X, and since I'm conditioning on X, I don't care about the variability in X. Okay, because a condition on X means X is fixed to some value. In this case, Y is a random variable, right? It's just something plus a normal random variable, then it's going to be a random variable. So I tell you what the random variable Y is given X, but I'm not telling you what what's the distribution of X itself is. Okay, so I'm telling you in linear regression, I'm only telling you P of Y given X, but I'm not telling you P of X itself. If I tell you P of X, then it becomes a generative model. If I don't tell you P of X, if I only tell you this, then it's even if it's a linear regression model, it's not generative. Okay. Is logic regression generative? It's not. I just told you that even in logic regression, we're only specifying P of Y given X. We're not saying anything about P of X. Whereas, so you should go back and check logic regression versus linear discriminant analysis. They're very similar, except linear discrimination analysis specifies a full joint distribution, okay? Because there's some additional normality assumptions that it normality. Yeah, I mean, so I don't recollect the exact assumptions here, but one specifies joint distribution. Logic regression only specifies the conditional probability. Okay. Let's come back. Sorry, I'm zooming out too much. Okay, so I wanted to give in the next task a quick, I guess, description of what is called a language model. Okay, and in particular, we're going to use Markov modeling to answer that as a solution to the language modeling problem. A language modeling problem is essentially the problem of characterizing the your language in terms of conditional probability. So a language model's base object essentially should be what is the next word given previous words. Okay. So when people say language model, they are essentially talking about this. So some object, maybe it's a function, maybe it's a machine learning model, whatever it is. It should be able to do this, which is to say, given if you see these three words in a sentence, what is the likelihood of the fourth word being something? Okay, that's what a language model is. And I mean, whether it's a character level model, character just means at the level of alphabet. You can have word level language models where the previous things that you see are previous words, or you can have a character level language model where the previous things that you see are the previous alphabets. Okay, character level language model makes sense when you're forming. Okay, character level or word level or sentence level, whatever it is. Basically, as I said, the base object is some sort of a conditional probability of next thing given previous things, right? So let's pick a particular level of language model. Let's say it's a character level for simplicity. Then if you have this object, which is the one in the red box that I'm showing, if you have that object, then you can actually generate new sequences of characters, right? If I start with the character, let's say A, then and I can sample from this conditional probability, then I can get the next word. Next word could be a space, for example. There's a space here. Next character could be a space. And then given A and a space, what is the most, you can sample the next character, and that could be, for example, C, just as an example. So you can actually generate sequences of characters, and therefore you can generate sentences if you had access to a good language model, okay? And since you're sampling from this, you may get different sequences every time you sample from that. Now, but how do I get this object? What's the probability of next word given previous words? One simple idea is to use, what is called Markov modeling, right? Markov modeling, Markov just means memoryless, which just means that the probability of the next word. So the moment I put a probability here and something to the left side of the argument and something to the right side of the argument, they're all random variables. Okay. Now Markov model is just saying that, or Markov modeling, the underlying idea is that the probability of this next word, which is a random variable, only depends on the previous immediate word, for example, or the previous two immediate words, and not everything else before that. So that's the memorylessness. It's just saying that. Let me use not that side. Okay, maybe. Oops, I think I wrote quite a bit there. Okay, let me just write it here. Markovian property just means the probability of the random variable, let's say xn, given xn minus 1, xn minus 2, all the way to maybe x1. For example, if it's first order Markov, then it's just probability of this conditional probability is assumed to be like this, xn given xn minus 1. So given xn minus 1, the previous random variables, what the values they take don't matter. Okay, that's what Markov model just means. Okay, now let's come back here. How can you build a character level language model using Markov modeling? The idea is very simple. If you have training data, and we always start with some training data, which is the sequences of characters, what you can do is make some assumption. So because we said we're going to use a Markovian assumption, so let's say we pick an order 2. Okay, so only the previous 2 characters matter to determine the probability of the next character being something, and all the characters before that do not matter. Okay, so that's an assumption. Under that assumption, let's say you have a training sequence HELLO. Okay, those are the sequence of characters. Then what you can do is compute, for example, this conditional probability. What is the probability of L given H and E? Okay, so that you can compute. I mean, this is an example which will positively add towards both the numerator and the denominator here. But you have a different example. Let's say, train. So you do not see L or H or E. So this example is not useful, right? Maybe there's another example where it is. Thesis. Okay, so there's H and E there, but the next letter is S and not L. So that would be a negative example while computing this summary statistic. The summary statistic is just saying pick out all the examples where you see H and E, and in those examples, if wherever you see H and E is the next letter L. Okay, if the next letter is L, count up. If the next letter is not L, ignore, and then you divide it by all the examples where you see H and E. Okay, so that gives us an estimate of this conditional probability. And if you can compute this type of conditional probability for all combinations of letters, okay, all combinations of letters, then you can somehow have an object which will be able to replicate this guy, right? Like not just L given H and E, probability of A given B and C, probability of A given D and E, many such things. If you compute all of them, then you'll have an object like this, right? And if you have that object, then you can sample from all these conditional probabilities. Because these are discrete random variables. Um, um, Discrete or probability mass functions. Essentially, you can easily sample it on a computer, and so you can generate sequences of characters. Okay. So, any questions about this part of how to? So, what is the language model, and what is how to build a character level language model using Markov modeling? Okay, if there are questions, just ask it in chat. I'll try to pay attention there. So I want to start the next model, but I want to take. Okay, let's start the next model after taking a quick break. So we'll resume at 4:44. Okay, 4:44. In the meantime, if you have any question, post it here. Okay, so welcome back. Okay, so that was what is a language modeling task, and very simple example, very simple solution strategy using just Markov modeling, or basically keeping empirical statistics of conditional probabilities. Next, I want to talk about a different task, which is clustering documents, or clustering documents, tweets, sentences, or paragraphs. All these are very similar tasks. And so, as you know, clustering is an unsupervised learning task. Yeah, so clustering is an unsupervised learning task. So we don't have labels. And so first I'll start with describing, so we'll look at another generative model. And because a generative model generally describes joint distributions among a bunch of random variables involved in that problem, we'll look at one particular type of joint distribution, and a part of the joint distribution is going to be described using a Dirichlet distribution. Okay, so some random variables in that joint distribution will have what is called a Dirichlet distribution. So let me just describe what the distribution is, at least in terms of pictures. So Dirichlet distribution is a distribution over over vectors. Okay, so think of a distribution over vectors, which means that if I draw a sample from this distribution, I get a vector. Okay, for simplicity, let's say it's 3 cross 1, and that's where these pictures. I'm going to explain these pictures pretty soon. Let me not put those lines there. It's going to be 3 cross 1, let's say. So it's going to produce numbers, A, B, let's say C, some 3 numbers. The cool thing about this distribution is that it's going to produce this number such that the numbers add up to 1. Okay, so A plus B plus C is equal to 1. So it's going to produce all these vectors, right? 3-dimensional vectors whose who sum up to 1, and also that A is going to be greater than 0, B is going to be greater than 0, and C is going to be greater than 0. So it's going to produce samples, or the random vector that it produces. It satisfies these essentially constraints. Okay, so and you can recall that these constraints are essentially the constraints for a probability mass function. So PMF is essentially defined by a bunch of numbers such that those numbers are positive and they add up to positive and they add up to 1, right? So this Dirichlet distribution is really producing a probability mass function. Okay, so these pictures here, these 6 figures are showing the Dirichlet distribution in a 3-dimensional space. So let's focus on the bottom left figure here. So this figure is showing a plane, okay, a plane segment, which is this. Okay, so so the what is this plane here which I've shaded? It's a plane. It's a segment of a plane, and the plane is intersecting the x, y, and z coordinates at these three locations. Okay, so this figure is just showing a three-dimensional space where there's a segment of a plane which is like a triangle. If you look at it from the front view, then it just is a triangle. But if you look at it in 3D, it's a slice, which is intersecting the three axes at these coordinates. Okay, and so every point on this plane is actually so let's say this is so every point on this plane, sorry, is such that it sums up, their coordinates sum up to 1. Okay? So for example, if you look at this corner points, clearly the corner points definitely sum up to 1 because 0 plus 0 plus 1, for example, is 1 and so on. Okay, so all these corner points definitely are probability mass functions. So probability mass function vectors. Similarly, every point on this plane is also a probability vector. Okay. Now, the digital distribution is therefore a distribution over these points. Okay, so if I convert these, this triangle into 2 dimensions, right? Right. By the way, a plane in a 3 dimension is essentially a 2-dimensional object. So if I make it a 2-dimensional object, there's a bunch of points on this. So the digital distribution is actually a distribution over these points. Okay, so for example, some points are more likely than some other points. That's captured by the distribution. Okay, and so if you look at the bottom left figure, it's trying to show a peak here. So it's trying to show a peak here where points over here have a higher probability than points over there. Okay, so that's the triangle in 3 dimensions. Okay, that's what a digital distribution is. So with that, that just at least tells you there's some digital distribution involved in this modeling of, clustering a bunch of, let's say, articles into clusters. Okay, so in particular, there's also a word latent, and I'm going to describe why something is latent. Latent just means hidden. So just like a hidden layer, you can just call like a feedforward network, the hidden layers as latent layers. Okay. So now let's talk about, as I said, this is a generative model. So how does it model so since it's a generative model, it should also tell us how to generate documents, okay, generate articles. And then it will also let us cluster these documents as well. So, and by the way, this is an instance of a topic model. Okay, there are many topic modeling techniques, but this is one of them. And basically what they do is given a bunch of documents, you try to figure out topics in these documents. So for example, some documents are about politics, some topics are about, some documents are about religion, some documents are about sports. So once you get the topics, you can also cluster these documents, right? So some document will have a lot of information about sports. Maybe it's a sports topic based document, okay? So and topic modeling is a part of many interesting applications, information retrieval. For example, if you're searching for documents on the topic sports, then hopefully you get the documents back which are related to sports and not other things. And you can also summarize documents according to the topics that they belong to, and you can also classify documents. Okay, so when a new document comes, okay, if you have the topic model, somehow you learned the topic model from previous documents, then you can answer this question: what is this document about? Okay, you can say maybe this document is about weather, finance, and sport in these proportions. Okay, so let's look at what the model itself is. It's a generative model. So remember, in a generative model, I have to start with some random variables and describe how the subsequent random variables are generated. Okay, so I'm gonna tell you what the random variables correspond to a document look like. Just like in Naybase, there are random variables which are indicators of whether the word is present or not in an email. Here, it's going to be very similar. So let me start with the starting point, which is first step. Okay, in a generative model, I'm going to describe a way to generate a document. Okay. First step, you sample a topic distribution. So topic distribution, let's say we assume for simplicity, let's say there are only 3 topics for simplicity for this example. Then we need to generate first a topic distribution. So it's going to be a 3-dimensional vector, okay, with theta 1, theta 2, theta 3. And it's a topic distribution, and therefore it's a probability mass function. So it should sum up to 1. Theta 1 plus theta 2 plus theta 3 should sum up to 1. And because this is the type of vectors that are generated by a digital distribution, we're going to use a digital distribution to first generate this. Okay, so theta is a random variable here. Okay, and digital distribution will have its own parameters, so let's not worry about that. And these parameters actually describe are actually the parameters of the topic model. But those are not, let's not assume that they're random. So given some parameters of the digital distribution, I can first generate a topic distribution. Okay. And then theta is a random variable. Now what I'm going to do is I want to produce an n-length document. N-length document just means I need to produce n words in my document. For simplicity, I'm just fixing, let's say n is known, okay? It's fixed, it's not a random, every document has the same number of words for simplicity here. Then first what we do is for each location, first word, second word, all the way to nth word, I'm gonna sample a topic of the ith word. Okay. So for the first word, I'm gonna draw a sample from theta. Remember, theta is a topic distribution. So if I draw a sample from this distribution here, so let's say its distribution is saying topic 1, topic 2, and topic 3. Okay, so topic 1 with probability theta 1, topic 2 with probability theta 2, topic 3 with probability theta 3. Okay, so first word I draw from theta. Okay, I draw from this topic distribution. I get that the outcome is 1, which means that the first word first word's topic is gonna be topic 1. Okay, I'm gonna assume that. Remember, we are generating a model, so generating a document. So first, what I'm saying is I'm gonna draw a topic distribution such that topic for, let's say, weather, sports. What was the 3 things? Weather, finance, and sports is and the 3 numbers. Let's say 0.3, 0.2, and 0.5. I first draw what is the topic for the first word. Let's say it's topic 3. Then Z1 is equal to 3. Okay. Similarly, I'm going to draw another, draw from the topic distribution for the second word. Maybe the topic is 2, then Z2 is equal to 2, and so on. I'm going to continue this all the way to Zn. First, I'm going to generate these values of these random variables. Then, given these Z's, I'm going to fill in the actual words in this, like it's a fill in the blanks. Basically, I know the blanks, there are n blanks, and each blank, I know what the topic it should be because I just sampled from theta for each location. Now I want to fill in the word itself. So for that, I need another object, which is for every topic, I'll have a corresponding distribution on words. So let's say I have 10 words in my vocabulary. Okay, so 10 words in my vocabulary. So for every topic, there are 3 topics here, 1, 2, and 3. I'll have a beta 1, beta 2, and beta 3 as 3 probability mass function vectors. Okay, so again, these are 10 cross 1, 10 cross 1, 10 because, sorry, oops, I went all the way. Yeah, what I'm saying is this is 10 cross 1. Okay. So beta 1, beta 2, beta 3 are again probability mass functions. Okay, what is the entries here? Let's say 0.1, 0.01, 0.9, and so on. So these are probability mass functions over words. Okay, I have first word, let's say the second word is like a sport. Third word is, let's say, weather, let's say temperature, and so on. So you can see that beta 1, if there are words which are corresponding to weather have higher probabilities, then beta 1 maybe corresponds to the weather topic. Okay, so because now I've already designated what topic each word should be, I just go back to beta and draw a sample from the appropriate topic. So if the first word happens to be, as I said, is from topic 3, let's say the topic 3 is from sport, then I can draw a word from these vocabularies. But beta 3, the probabilities will be such that the sport words will have higher probability of occurrence. Okay, so that way I'll pick word 1. Okay, and that way I pick all the n words, and that collection of words with no particular ordering between the words, and therefore they don't make any grammatical sense. That's how you generate a document using LDA. Word to topic in here, is it arithmetic across rows of these three columns? So you're talking about these three here. So beta 1, beta 2, beta 3. No, there's no arithmetic. So remember in step 2, we said, oh, what is the topic of each word? That's all we did, but we didn't specify. At the end of the day, we want to get n words, okay, which is what a document is essentially. But there is no ordering between these n words. That's a very big limitation for this model. So in the step 3, we are trying to generate words. We already know which topic the word should belong to, but we don't know what the word itself is. These three vectors here, beta 1, beta 2, beta 3, are essentially probability mass functions. So they are probability distributions over the vocabulary. I just chose vocabulary size to be 10 here. So since I know that the first word is from topic 3, then I'm just going to look at beta 3 and draw a sample from it. It's just a probability mass function. If I draw a sample from it, it'll tell me some coordinate. And that coordinate, whatever the word is corresponding to that coordinate, that's the word in that location. Okay, good. So that's LDA. That's the generative part. Okay. So yeah, this is what I just mentioned, right? And so sorry, I think the beta 1, beta 2, beta 3, I should have shown it here. Beta 1, beta 2, beta 3. So it's just basically a distribution of like a word and it's what's the probability associated with that word. So these are large lists. I just said in the previous example it's 10 cross 1 each, but it doesn't have to be. Okay. So given z is equal to t just means whether it's topic 1, topic 2. So this t is 1 or 2 or 3. It's just saying if it's topic 1, then just look at this list, basically probability of each word. And if it's 3, just look at this list. Okay. So that's how you get a document. So if you go back and look at the full picture, all we're saying is each word. So if you have a document here, right? Each document is essentially a mixture of topics, right? Mixture of topics where each word is essentially which topic it belongs to and the probability of the word in that location. So it's not each word, sorry. Each location, you have a random variable which says which topic it belongs to, and the word in there is from the appropriate probability mass function. So that's the generative model. Okay. Now, what are the parameters of this? Okay, so this picture is just trying to show that, okay, some words come from different topics. The color coding here, yellow, blue, and red is just from the three different topics here. Somebody has a question? Okay. And here they're showing all, if you have more than 3 topics. So remember for naive Bayes, I had drawn a diagram with the random variables. Here also you can draw the diagram, which the diagram is going to be a graph. But the simpler version of the diagram where you fold in a bunch of random variables is what is shown in this figure. Okay, so let me explain. So you start with alpha. Alphas are the parameters of the Dirichlet distribution, and you start with beta, which are the topic word distributions. So these are the parameters of this model. So given alpha, the generative procedure would be you draw a sample for a given document. Little d represents document index, let's say first document, second document, and so on. You first generate a topic distribution for the document. And then for each word location, so I only want to produce n-length documents. For each location, I first produce the document. So I first produce a topic for each word location. And then I'll fill in the word itself. But to fill in the word itself, I need the topic word distributions. Okay. So the the star marked ones are the ones which are the parameters. Now, given a bunch of documents, the generative procedure talks about how to go from one random variable to the other, which essentially means the generative procedure is telling you the full joint distribution between all the random variables involved. Okay, so the latent Dirichlet comes from the fact that what you see at the end of the day is just a document. You don't see the theta d, you don't see the topic, the location specific. The topic, the word topic random variables. Okay, because you don't see theta d and theta zid. These are latent, as in they are not observed essentially in the data. So now, how do you learn? Since I said there is a joint distribution between theta d, zid, and wid. Okay, which is what we have described so far. We have observed W's, and so we can find thetas. We can find, given a document, we can find theta D if you know the parameters. Let me just change the parameters to, it's a phi. Okay, let's say phis are the parameters. Okay, let me actually not use phi. Parameters are alpha and beta. Okay. So we have this joint distribution. Now, if I know a given document, let's say WID is given, if I know alpha and beta, I can find, I know the joint distribution parameters, I know a part of the joint distribution, I can tell you what's the most likely topic distribution, what's the most likely assignment of the words, location of each words to topics, okay? We generally don't care about this. All I'm saying is we can compute theta D given WD. So probability of theta D given WID, just all these words, if I know alpha and beta. So alpha and beta are parameters of this probability. Okay. So that we can, so given the model, we can find the topics of any new model, the topic distribution for any model, any new document. Now, how do you learn alpha and beta? You can see that this problem becomes a problem where you're only observing part of your generation, right? If you observe theta D, ZID, and WID, then you know how to fit alphas and betas. You can just do maximum likelihood estimation. Okay, but because a bunch of the theta Ds and ZIDs are not seen, but only the document is seen, which is only part of the sample here, you have to do a little bit more. And there's this. I think we've used a technique called expectation maximization. At least some of the folks in 575 might have seen it. So EM is a way to deal with likelihood estimation when you don't observe part of the data. Okay, so you can use EM to estimate alpha and beta, and we're not going to go into the details here, but this is one model. But I wanted to show this model because in this model you're not really explicitly exploiting the relationship between words. Okay, and that was the theme. Even in Naives, we were not explicitly exploiting relationship between words. And same with Markov models, the language model based on Markov modeling, or this latent data allocation. I'll skip the slide. This is just showing two different generative models. But LDA is also called an admixture model, and it has slight difference with a mixture model. Okay, but you can read this slide, or we can come back to this towards the end. It's a very simple. So the other model is actually a much simpler model than LDA that I just described. So it's probably easier to understand. Okay, let me go over to the next model. So any questions at this point?
So the article or blog we generate from that, is it going to make sense grammatically?
No, it doesn't. So that's why. So there's a huge mess. So maybe language models help you there, but LDA is just really not a model for generating new documents. It's a generative model. So therefore, that's why I told you how to generate a document. But the document that it generates is just a collection of words. Okay.
Okay.
It really doesn't. There is no order relationship, first of all. So which is another big issue with both Naives and LDA, for example.
Okay. And the topics that we choose based on the theta vector, is it going to be proportional to the probabilities, right? The first.
Yeah, so these topics, we don't choose the distributions. So these are parameters that we need to estimate from some existing collection of documents, okay?
Okay.
And the number of topics you choose based again on fit. If you choose more topics, then maybe you have a higher log likelihood fit in training, but you're not able to get a good log likelihood fit out of sample and so on. So this how many topics to choose is all data driven.
Okay.
In the sense, you need to choose, just like in KNN, you need to choose what is the K of the number of nearest neighbors you're looking for. But these are parameters of the model, and you need to estimate them using existing documents.
Okay. Okay.
Yeah.
Cool. Yeah.
But once you get these distributions, then maybe you can sort them according to those words which have the highest probability, and then maybe those words give you a sense of what the topic is about. Maybe some that's how you post hoc interpret these topics to be sports versus weather versus something else. Okay.
Yep.
Okay, so let's go to CNN-based sentence classification, and it's actually a teaser topic because it requires word embeddings, which I'm going to talk about in the next part. But basically, we're going to use CNN to do sentence classification. So what is the input? The input is a sequence of words as a sentence, and the output is a simple class label. For example, the same thing as before, like Naybase was essentially also doing essentially something similar to sentence classification, because it's classifying an email, which is a sequence of words, and the class label was spam or not spam, right? But here it's going to take into account the sequence aspect of the input, okay, which was not the case for Naybase. So that's why I just wrote a baseline here. You ignore the sequence, you ignore semantic information, and you can treat the input as a fixed length bag of words. It's exactly what Naybase did, and then you just want to go from a fixed length bag of words, let's say 001, 010. Some words present are 1, and from this you want to go to a label which says, positive sentiment or negative sentiment, for example. Because that's an example, a specific instance of sentence classification, right? You have a sentence, you want to figure out whether the sentence is talking about something positively or something about, is talking about something negatively. Then that's a 2-class classification problem. So, so that's what you can do. So it's a fixed size input, which is just a vocabulary size vector, and the output is just the number of classes you want to classify the sentence into. Okay. So it's not taking into account any ordering, and the encoding is also quite primitive. So the next baseline is actually the next baseline, as well as the CNN-based solution. They will need what are called word vectors. And for now, I haven't told you exactly what word vectors are. That's actually, we're going to talk about it quite in length pretty soon. But just think of words. Okay, in the language, whatever be the words, this sentence, sentence. So this is a word which will have a vector, and a sentence is a word which will have another vector. Okay, so these vectors will have, vectors have a collection of numbers. The numbers in these vectors we will figure out later. Okay, so they will be learned somehow. They are data driven. They're not predetermined. And remember, in one-hot encoding, this would be encoded as something like this, and sentence would be some word, like this, right? So these are vectors corresponding to the one-hot encoding of these 2 words. Let's say if our vocabulary was of certain size, let's say 1, 2, 3, something like 7. Okay, 7 cross 1, 7 cross 1. If our vocabulary was 7 cross 1, then one-hot encoding would be something like this. Word vectors are essentially a generalization of that, in the sense that we'll have vectors of some length, maybe d cross 1, t cross 1, some arbitrary dimension, and these numbers will be learned using machine learning, and we'll talk about it in length. But a baseline way to do sentence classification, if you had access to these vectors, let's say somebody gave you these vectors corresponding to every word in your vocabulary, somebody already gave you. Now your question is, how do you classify? What you can do is you can take the weighted average. One simple baseline is take a weighted average of the word vectors as a single vector. So each vector is of same length, d cross 1, d cross 1. If there are 10 words in this sentence, you just average those 10 vectors. Okay, just element-wise addition divided by 10, essentially. You lose the word order here, right? Once you have the fixed length d cross 1 vector, again you're going to this let's say 2 cross 1, 2 classes. Let's say 2 classes that you're trying to find. You're gonna again somehow go from this d-dimensional vector to a 2-dimensional vector, and that you can do again using simple logistic regression or any of these existing methods. Okay. How will this handle? So somebody has a question. When the input size is fixed. So remember, so that's why this is an example baseline I'm talking about. Here, whatever be the number of words, all the words are represented as d-dimensional vectors. And I'm saying you take an average of these vectors. So if you take an average of these vectors, you're really, even if it's 10 words, even if it's 20 words, ultimately you'll get a d-dimensional vector, right? So that in that sense, the input is fixed. Okay, the size of the input is fixed. It's only be d-dimensional. If I take an average of all these vectors. Same thing with this baseline 1. If I had a, because I'm looking at a vocab size vector, the vocab size is, it's fixed irrespective of whether your sentence has 10 words or in the vocabulary, or it has all the words in the vocabulary, right? So these are simple baselines. The second one requires word vectors, and even the CNN one requires word vectors. And it's a teaser for for us to learn word vectors later. Okay. So let's go to CNN-based sentence classification because it's a little bit non-standard. So in NLP, CNNs were first used effectively back in 2014, about half a decade ago. There are many methods to do sentence classification, as you know, all the from preliminary simplistic methods to many complicated methods, including some methods that we'll see not in this lecture but maybe next lecture. But so what does a CNN do for images? So let's recall what CNN convolution layer does for an image, and then try to think about how do I use that when I have word vectors and I'm looking at text data. Okay. So an image, just to recall, we'll have what is called a filter. So here we have a 3x3 filter. Let's say our image is depth 1. Okay, for simplicity. For simplicity, then our filter will be of the same depth as the input image, in this case depth 1. Let's say our filter is 3x3, then every filter will produce one output matrix, right? So in this case, let's say since the filter is 3x3, let's say it's at the top left, then just element-wise multiplication, add up the output, and that's 4. Okay, so that's the one entry by this filter by being in the top left. Now you move to the center, there's going to be another entry, and if you move to the right, there's going to be one more entry, and so on, and keep move a little bit down. You basically you're sliding over the whole image. Okay, so that's just to recap what a filter or con layer will do. The whole point of using filters is that they help in dealing with location invariance. So if there is a important feature which is useful for classification, whether the feature, as in the image level feature, like an edge or a circular thing, irrespective of where it is on the image, if you can detect that, you can classify your image as something or the other, right? One class or the other. So that's what the filters capture, the con layer captures. And it also captures compositionality, where the filter, let's say if you have a bunch of con layers, the con layer, let's say the second con layer looks at only a small area of its input tensor, but this input tensor, if it's also con layer, it looks at a small area of its input, and so on. But as you can see, this neuron here, this neuron actually is able to see a lot more than the immediate layer. So in the sense, there's some composition going on. So in the sense that the layers towards the back, as in the later layers, are looking at bigger and bigger areas of the input image. Okay, so there's some composition of lower level features, maybe edge detectors into face detectors at higher and higher layers. Okay, layers closer to the output. Now, what we're going to do for sentence classification is, first prepare the data and then talk about how convolution applies to it. Okay, so what is our data prep? We are just going to think of each row as a representation of each word. So let's actually go into details with this example. So let's look at this part. Okay, so this part. So let's say the sentence is, I like this movie very, very much. Okay, so what we're going to do is for each word, we're going to, as I said, a primitive for this CNN-based sentence classification, at least for our narration, is that we already have word vectors corresponding to it. So let's say I have a 5-dimensional word vector corresponding to each word in my vocabulary already. And we're going to discuss how to get these vectors later, in fact, the next part of this lecture. Okay. So let's say I have 5-dimensional vector. Then for like also I have 5-dimensional vector. This I have 5-dimensional vector, and so on. So there is a, the sentence has this order relationship. I don't want to permute it, right? If it has a particular order relationship, so I'm going to create a matrix with that, exactly like that, where the first row corresponds to the first word, second row corresponds to the second word, and so on. Okay. I'm not going to flip the rows of this matrix. Okay, and that's going to be important. And given this, sentence, I have this matrix. And the moment I have this matrix, you should already see that I have something like an image. Okay, image with depth 1. Okay, and that's exactly what's going on. So with one more caveat is that we're going to look at a certain size filter. Okay, so first thing you notice, it's like an image, right? Image with rows. So image with no depth is essentially a matrix, and that's what we've got in step 1, data prep. Right, with the word vectors. Now in step 2, we want to use filters. Now what I'm going to do is choose filters with some number of rows, okay, some number of rows, let's say alpha, but I will always keep the number of columns to be the same as d. Okay, d is equal to 5 here. So I'm going to keep the filter size such that the height of the filter is some alpha. Let's say height of the filter, so actually, if you look at the focus on the second column here, where I'm underlining something, so you can see that there are actually 6 filters here. Sorry, 6 filters here. So this is a filter which has 2 rows and 5 columns. This is a filter which has 2 rows and 5 columns. This is a filter which has 3 rows and 5 columns. This also has 3 rows and 5 columns. This has 4 rows and 5 columns. And this has 4 rows and 5 columns, right? So each of this filter, now I have 6 filters, which means I need to get 6 outputs, okay? 6 output matrices generally. But since the filter width is the same as the input width, I'll actually not get a matrix, I'll essentially get a vector. Okay. In fact, you can think of, let's pick the last guy, the one I'm showing here, the yellow one, and let's create how does the filter slide. Okay. So this is my input, and I have a filter which has 2 rows, right? I mean, so this is of I don't know, is it 7? Yeah, it's a 7 cross some d dimensions, and this is 2 cross some d dimensions. So d is fixed, so let's ignore it. So the way we're going to slide is, first we're going to start from the top. So we're going to slide on the first 2 rows. We're going to produce one number, and then we're going to go on to this next 2 rows. We're going to produce one number with some overlap. Okay, so stride is 1. Okay, and then we're going to go to the next 2 rows, and get one other number, and so on. So you can imagine that, right? So take this yellow block, put in the top 2 rows, do element-wise multiplication, generate one number. Okay. Take the same, the yellow guys, the yellow matrix, put it on the second and third rows, you get the second number. And now if you do the same thing with third and fourth rows, you get the third number, and so on. Okay. So that's how you generated a vector from a single filter. Okay, so this filter of size, with height 2. Similarly, filter of height 3, you'll have a number, you'll have a bunch of numbers, but I think, but because the number of rows here is 3 versus the number of rows here is 2, the length of the vector you'll get is different. Okay, so for example, for 2, the number of rows you have at the output of this filter is 6. Okay. Whereas when you had a filter of size 3, the output is of size 5. When you filter of size 4, the output is of size 4. Okay. So once you have these vectors, these are the outputs. I mean, clearly the filters were of different sizes. They were not of the same sizes. Therefore, the output matrix, but one of the dimensions is just 1. They're of different lengths. Okay. Now, what you do is, once you have these vectors, there are various ways to compose them together. So you can just do you can do max pooling, which is the moment you have these vectors, you can compress them into a single number, like take a maximum of them, take the maximum of them, take the maximum of them. You have 6 numbers here. From 6 numbers, you can just do a fully connected layer to get to the 2-class classification problem. Okay. So is the explanation clear? Any questions at this point? So this is an example architecture for how to use a CNN if you have word embeddings, or if you have word representations of the vector. Okay, and what's the new thing that this is doing compared to many of the previous techniques is that it's taking into account the order relationship, order or sequence, right? If I give this particular sequence, I like this movie very much, that has a specific matrix, and the way you convolve with different filters will give you different numbers. But the moment I permute, let's say I do much, this very and then movie, then it's a different matrix. And then once you do this filters and slide these filters, the numbers you get is very different. Okay, so it's actually taking into account the sequential ordering of the words. Okay. Any questions of that part? So that was a teaser for us to understand how do you get these word vectors, and we're going to talk about that now.
So is there anything like visualization that we can see, that what are the starting layers to versus end layers, like image?
Yeah, we can. So, in fact, I think I have linked this. Um, let's see. So I have linked this um, the corresponding Python IPython notebook, which does CNNs for sentence, which actually you should read the paper as well. I think if you look at this link I have, so you have a few well-known tools for text processing. Spacey is one of them. You can read this very nice tutorial on LDA.
Okay.
And then additional reading for CNN sentence classification tasks. There is two papers, okay, and both are from 2014 and 2015. If you actually read the paper, you'll see that it's a very simple paper, and they do go into the details of. Uh, it's actually 6 pages, and they describe exactly what we just discussed. How do you go from a representation, for this sentence all the way to a classification problem. Although they may not have in this paper might not have visualized what's happening
Yeah.
in the intermediate layers, but you can do it. And actually here the objective was to show that if you just do CNN based simple model like that, it actually gives you much better performance. Actually, let me just uh, show the performance. Okay, this has a lot more details. Um, yeah, I think maybe it's the other paper, which actually shows you that how do how do CNN-based techniques compare with other techniques. So this is, you can see that this is some modern SVM-based model, and there are some other models. These are the SVM models, and how do they work? Okay, but if for your question about visualization, I mean, this paper is not going to show you that by itself, but this paper has been implemented. Actually, I think that was the second link, which is what I wanted to show. Um, I think it is the, yeah, I think it's good to read these documents to see if they have done that. Okay, that image is from this paper. Um, yeah, so they're showing how a bag of words SVM, and then how does these methods work? Okay, um, yeah, word vector SVM. So which is basically what using word vectors with SVM and so on. So maybe these papers don't show, although they do show some other outputs. What you can do is pick this particular repository. So you can see the link here, right? So you can open it on Collab. So last time I opened our own repository to show you the CNN classifier, right? How, very quickly how it was. So you can look at, so that's what I did. I just did file uh, open notebook and went to GitHub, and then you can copy that link here. Okay, that link on our webpage, and you can just pick the fourth uh, notebook which is related to this. Okay, now you can look at other ways to do sentiment analysis as well if you want, including, I think there's also transformers and so on. But if you go to here, then you actually see what the model is, right? So they're using torch and torch text, essentially PyTorch, and they're describing what the model is actually doing, how the convolution operation happens, and then they actually show you the model description. Remember, I think by this time, or maybe by next assignment, by the time you finish it, you'll be familiar with exactly how to extend the class NN.module to create your own neural network architectures. Okay, and you just need an init init function and a forward function. Forward function just produces the given an input, produces the output. Okay, so return the output class, for example. So here, when you train, let's say you train this model, so it's just a description of what the model is here, and okay, once you train the model, you will have the weights in the model. Then you can pass each individual sentence. You get the activations at all the hidden layers. You can look at some empirical statistics the same way we did for images, right? So same way we talked about doing it for uh, images in like, for example, using occlusion. You can occlude words and see if the sentiment is still positive or not, and then project the activations down to a low dimension to see if positive and negative sentiments cluster into two clusters nicely or not, and so on. Okay. I mean, they don't do it in this notebook, but you can extend that once you do the training. So you don't touch anything here. Once you finish the training, so after all this, then you can, once you have the model, you can do all this debugging. Sorry, that was a long-winded answer, but I wanted to show you that this notebook is available, which does CNN-based sentence classification. So try to go over it. There are two takeaways. One is to understand what CNN-based sentence classification is doing. The second thing is also to understand how a PyTorch, notebook-based, neural network training looks like. And we discussed the CNN fine-tuning as well as feature extraction, the transfer learning notebook last time. So that notebook for vision and this notebook for text will give you a sense of what are the preliminary components. Okay.
Okay. Yep.
So there's a question. So I hope that answers your question. There's a question here which is on max pooling helping to pick the best sequence. No, actually the max pooling is just to reduce the dimensionality. I think. The max pooling is just to reduce the dimensionality there. So you can actually remove the max pooling and see and connect a bigger fully connected layer. So let me just come back to the diagram. Yeah, so these max pools are just to reduce the dimension, and that's essentially what the objective of max pool is, to reduce the number of numbers to compute for later on, because ultimately you have to produce two numbers, scores, from all the numbers that you started with, right? So that's an effective way to reduce the number of numbers. Okay, any other questions at this point? Okay, so let's actually sample size. So there's a question about sample size matters. Yes, of course. So you can actually, and I think in the first exercise, okay, in the first assignment you did not do this, but you can actually, whenever you have a data set, you can actually look at the trend with respect to size of the data set. And hopefully at some point the size of the data set should not matter. But there are, in fact, the whole point of neural networks is that as you increase the size of the data sets, the performance increases for neural networks. Whereas there are some, shallow models, the performance kind of, tapers off. So that's in general very broad, I guess, trends about why neural networks have higher capacity than shallower models like SVM, let's say classification or whatever. But for any particular model, any particular data set that you have, it's always good to look at the impact of size of the training data set on your accuracy numbers. Because sometimes if you see that if you double the size of the data set and you have double the accuracy, that means that maybe collecting more data is useful for you to increase the accuracy than to fit a more complicated model. So but yeah, sample size, analysis, it's not there in this notebook that I showed you, but sample size does matter in accuracy, in getting good accuracies. Okay, let's talk about embeddings. So basically, I've already told you what embeddings are, in a couple of places. Embeddings are essentially, from symbols to vector representation of symbols. So we've already done vector representation of not symbols but images. Remember, if you had this feature extraction part in the last lecture, it was just basically going from an image to, for example, if you use AlexNet or even VGG 15, 16, or 19, you essentially get a 1000-dimensional or 4096-dimensional vector. Okay, the activation, pre-activations before the last fully connected layer. So so that vector representation is essentially an embedding of the image. And then we said, okay, we can project that embedding, that higher dimensional vector, to a two-dimensional vector, sorry, into two-dimensional space to see whether similar images or images of the same class are clustered together or not. Okay, that was one debugging technique that we discussed. Similarly, so for us, even with text, all we are trying to do is go from symbols to vector representation of these symbols. So for us, symbols are, for example, words. Okay, so that's what an embedding is. An embedding is just a vector representation. Now, but the way we get to those embeddings is going to be with a slightly different way, which is we want to ensure that semantically similar words. Okay, semantically similar words. Semantically just means the meaning of the word. It has, of course, a more precise definition, but for loosely speaking, similar words should be represented similarly, in the sense they should have similar vectors. So remember, in one-hot encoding, if we had the word dog, cat, and house, then the L2 distance between those two vectors, any two vectors, any two of these words, was the same. It was square root 2, right? It was square root 2 if the vectors were 1, 0, 0, 0, 1, 0, and 0, 0, 1 for cat, dog, and house. Okay, so but we want, because cat and dogs are maybe in the category animals, so maybe the vectors should be closer to each other let's say in terms of distance. Okay, that's what I mean by hopefully they're represented similarly. Maybe even they should have very similar, instead of 1, 0, 0 and 0, 1, 0, maybe it should be 1, 0, slight, third coordinate being slightly different, for example, for dog. I don't know. So this is the idea behind the generally what I call vector space models in NLP. And one way to get to these vector space models are basically these embeddings, is to start with this hypothesis that words that appear, so how do we say, two words are semantically similar? Okay, we could say two words are semantically similar if they appear in the same context. Okay, if they appear in the same context. So if a dog is affectionate and if a cat is affectionate, then maybe cat and dog are, since they appear in similar contexts, maybe there's a discussion about pets and they appear in different sentences, then they may share a semantic meaning. Okay, so there are two types of approaches to get to these vector space models, and one is a simple version that I'm going to motivate with, and then I'm going to talk about a prediction-based approach to get these embeddings or word vectors for the symbols or the words. Okay, and this is where we'll get Word2Vec. Okay, that type of representation. So I don't know if I have the discussion for. Okay, I think for PCA-based representation, what we can do is think of, let's say we have V words and we have V words, okay, capital V words, which is the vocabulary size. Then what we can do is just count the number of times they co-occur. Okay, so maybe word, word, the first word, and okay, let me use a word. So dog, and maybe cat here. Maybe they co-occur 100 times in my data set. Okay, so you just take that entry as 100 over there. Similarly, you just create a co-occurrence matrix. Okay, and then what you do is just create essentially a so you want to reduce. So what you want to do is do a matrix factorization. By which I just mean that you have this V cross V matrix. I want to create this. I want to assume that this matrix can be approximated using a V cross D, and then a D cross V matrix. So this is called an example of a matrix factorization, right? So it's just factorizing a matrix into two matrices whose product is the original matrix. So this is the count, bunch of counts for each pair of words, and these are one tall matrix and one fat matrix. Okay, so and PCA can also help you get these two matrices. Okay, so once you get these two matrices, essentially what you do is for each word essentially have a d-dimensional vector. Okay, so that way you can get a embedding or an embedding, essentially an embedding of a word, but that embedding of a word is such that two words which have high co-occurrence will have similar vectors. Okay, I mean, that's not given by just doing matrix factorization, but that's something that you can try to capture using this type of factorization. Okay. So I'm skipping a lot of details here because I want to get to the prediction-based approach to get to embeddings, and that's Word2Vec and all the subsequent embeddings that you might have heard of. So let's move forward. So just to ground the definition, a word embedding is nothing but a mapping from words to vectors. Okay. For example, let's say I choose the vector's dimension to be 300, then each word should have a 300 dimensional vector corresponding to it, right? For example, the vector for university would have a bunch of numbers like this. A vector for class will have a bunch of numbers like this. Okay. So how do we learn W? So W is a mapping, right? It's a function which takes a string as an input and produces a vector as an output. Now you can think of that as a function, or you can think of the W as some sort of a lookup table. So if I you can think of university and class as a key, and the value of this lookup table is this 300 dimensional vector for each of these words. Okay. Now the question is, how do we learn this lookup table, right? So we start with the same idea as before, that we want to we want to learn W. Okay, so how are we going to represent W? As I said, if it's a lookup table way of point of view, then W is just a matrix, right? If it's a lookup table, I just say, oh, word, what is the word? Class, right? Class is saying, class corresponds to the maybe the 100th row. Then you just look up the 100th row. It's going to be a 300 dimensional. So vocabulary science 300. So it's going to be a 300 dimensional vector, and you look it up and you give it back, return, right? So how do we get to this matrix of numbers? Okay, so where each row corresponds to an embedding or representation of a word. Okay, so what you can do is initialize such that W outputs random vectors, which means that you just fill in random numbers at each of these cells in this matrix. Okay. Then what we're going to do is try to update these numbers such that they capture the semantic meaning. Okay. So if two words appear in similar contexts, then their vectors, these 300 dimensional vectors, are such that they're very close to each other in some sense. Okay. It could be a distance measure, or it could be cosine similarity, or some way you can define similarity between these vectors of words. Okay. But to do that, to change these numbers, okay, we have to define a task, right? So we want to capture the semantic similarity between words, but how do we concretize the task? And we want to, we'll tell you, so we'll try to now define what the task is, which helps us get these appropriate word vectors. Okay. So here's one example task. Okay. So task will be to classify whether an input sequence of 5 words is valid or not. Okay. Remember, we want to get a semantic similarity between words. So in the naturally occurring, let's say we have training data, which is a sequence. Let's say our training data is a bunch of sentences. Okay, which means essentially sequences of words. So we have, let's say we crawled a bunch of articles on the Guardian or New York Times or something, and we have all these sentences. Now, so all the sentences have valid sequences of words, right? Valid sequences of words. Now, pick any 5 words in any subsequence from these sentences. The words which do appear in these articles, we're going to tag them as valid. Okay, and we can cook up some arbitrary sequences which are not valid, right? So we can modify. Let's say we picked a sequence of 5 words, and then randomly change one of the words to a completely random word. Okay, then more than likely that sequence of 5 words is not going to be, would not make any sense. And so you can just tag it as invalid. So I'm just saying that we can create these valid sequences of words and invalid sequences of words, and then we can just try to learn to classify them. So I'm trying to define a task, of a classification task in particular, so that I can get to good W matrix essentially. Okay. And I'm going to tell you how the matrix is related to classification task and how does it get updated pretty soon. Okay, so this 5-word sequence is called a 5-gram. Okay, that's the terminology that folks use. 5-gram, 2-gram, 3-gram, n-gram is the terminology. So let's say we get data from Wikipedia or New York Times, and let's say here's the sentence. Here is the example 5-word sequence. Operates the largest medical school. Okay. So what you do is you tag this as valid, Okay, its label is valid, basically, its output label. Then you take sentences and randomly replace, as I said earlier, with a random word. So for example, something like this, and just tag this as invalid. Okay, so now you have a two-class classification problem. And now what you do is, once you have this valid sequence, let's say now you have a classification problem, you have a training data. Now let's look at what one example does, right? So let's say operates the largest medical school. It's a valid sequence. So what we'll do is take the word operate, go to a lookup table, pick that row corresponding to operates. So that's a vector there. The next word is D. Pick that row which corresponds to D. There's a vector there. And similarly, there's going to be vector, vector, and vector. Okay, from a W matrix essentially. Then you have a bunch of these vectors, right? Now, somehow I need to use these vectors, these 5 vectors. And because I'm only working with 5 words, I can do anything, right? I can just concatenate these vectors one after the other. Maybe I'll get a large vector. And from this large vector, I need to go down to 2-class output. So I can do that using logistic regression or something like that. You have done this in assignment 1, right? So, but while doing backprop, what I'm going to do is I'm going to not just so I'm going to change these numbers so as to minimize my loss. Okay, so I picked these vectors, right? D corresponding to some vector that has some numbers. Those numbers I'm willing to change to minimize my loss for this example. Okay, so the mapping from these vectors to the two labels will also have some parameters. The classifier, for example, logistic regression will have its own parameters, theta, right? So I want to change both the entries of the W, the lookup table W, as well as the entries of the classifier C, so that I can do this classification problem well. And once I do that, hopefully the end result is that the entries in W are now really capturing what's are really capturing the semantically similar words to be together. Okay. The task itself, so that's not clear, but why the semantic similar words will have similar word vectors, and I will spend a little bit more time in the next few slides to explain that. The task itself is uninteresting, right? I just cooked up a classification problem, and the classification, whether we do really well in classification or not, is not really important. What is important is at the end of the day, whatever new numbers that you get in our lookup table, hopefully they have that semantic similarity aspect that we were hoping for, right? Okay, so before we get into how to interpret that we are actually getting semantic similarity, let's say we did learn some W. Let's now try to interpret whether it actually is capturing semantic similarity. Let's do that. Let's say that W is learned somehow, and let's now try to figure out how, whether it's a good quality embedding or not, whether the word representations, the word vectors corresponding to the words are good or not. Okay. Here I'm saying, say we learned a good W, we don't even have to say good. Let's say we learned some W, okay, the lookup table. Now, so there are 2 examples of lookup tables that you can easily get using, for example, Spacey, the package that's linked on the web page, or the other Python packages like GenSim, or or you can actually directly try to access them from their sources. Okay, these are just word vectors. Okay, for every word in the English vocabulary, there'll be a vector that you can get. Now, let's say you learned some W, so it could be the Word2Vec or Glow, or it could be some W that we created. How we can visualize to understand whether they are good or not, and we can do that by a technique that we saw last lecture, which is just projecting those vectors into 2-dimension. Okay, and this figure is unfortunately very unclear, but each thing here is essentially a word. Okay, so each thing here is a point on the 2D plane, and instead of drawing the point, we have replaced that with a word. Okay, and I think there's a source for this, so you can go to, I don't know if this source is still there, but it's basically a projection of all these embeddings into 2 dimensions to get a sense of whether all the words corresponding to similar things are together. And if you look at the slides, I have the link to the slides on the lecture page. You can see that these, for example, are numbers. And you can look at different regions to see what these words are. If similar words are together, maybe you got similar, semantically similar words have similar representations in the higher dimension, in whichever dimension, like in 300 dimension. Let's say W is vocabulary size 300. So maybe in 300 dimensions, the words, the vectors corresponding to these words have similarity, okay, with each other. I think I highlighted something here. Oh, okay. I zoomed into that thing which you cannot see. So these were numbers, and these are days, calendar days. So you can see that in the 2-dimension, I think this is with Word2Vec, or maybe Word2Vec. I don't remember now. But whatever the embedding is, in this case, you can visually inspect that the embedding is good. Okay. And there were some experiments that were done for embeddings. I think we are looking at, I don't remember which embedding this is, but you can try. So this is how you this is how you would post hoc try to understand whether you got a good embedding out of it, because the classification task itself is kind of not relevant to us. So once we have trained the W, gotten the really better lookup table than the random numbers that we started with in W, then you can, for example, let's say you did looked up what are the most similar words corresponding to the word France in this 300 dimensional space. You can look at the nearest neighbors, right? For example, for the nearest neighbors for France, you get a bunch of countries. For nearest neighbor for megabits, you get a bunch of technical measurement units, right? So that means that this particular embedding is good. So now let's come back to this question of why would such a classification task, this auxiliary classification task that it created, why would it give us words with similar meanings, or basically that appear in similar contexts? Why would they have similar vectors, right? So let's come back to that. And to this concretized example, if the sequence operates the largest medical school, you change it to operates the biggest medical school. If W maps biggest and largest close by, then you would say that biggest and largest are semantically similar, and therefore their vectors are similar to each other. Okay. Okay. So now let's come back to this question: why would the vector representations of semantically similar words be similar? So I think I'll skip this because yeah, I think that slide is we're going to revisit why the similarity aspect pretty soon. So let's move forward. So in our training data, so before I get to how similarity is captured, in our training data, you may ask how many sentences or sequences of words should we see to figure out this semantic similarity between a bunch of words. You cannot really see all permutations or all sequences of all words, right? So you will not see all sequences of all words, but we can still and you'll see that this classification task or this prediction-based modeling, it'll let us still learn semantic similarity of two words, even if those words did not exactly appear in exactly similar sentences. For example, I gave you this right this example where the 5-word sequences operates the largest medical school and operates the biggest medical school. You may not see the exact 2 sentences to figure out that largest and biggest are semantically similar, but still you will be able to generalize that largest and biggest have similar semantic meaning. Okay, and that's the nice thing about prediction-based learning of these embeddings. Okay, so here is just asking the question how much data do we need. So one last thing about embeddings, actually. Yeah, as I said, the question that we still want to answer, and I thought it will be pretty close, is that how are words getting similar vectors, right? How are they getting similar vectors through the auxiliary task that we saw? And we'll see, we'll concretize this. We'll answer this question using Word2Vec, okay? So model of this question, we are talking about a few other aspects currently, which was, first thing was, what is the quality of the embedding? Second thing was, do you need all combinations of words to be seen in your sentences. And the third thing is, which is true for, I think, or at least this is cherry-picked examples for Word2Vec, is that if you take differences of the vectors, you actually get similar vectors, by which I mean, let's say the representation for woman minus the representation for man. So there are two vectors of same dimension, 300 dimension. You subtract them, you get a residual vector. That vector will be similar to the vectors difference between aunt and uncle. Okay, so that's what they observed in a particular embedding, and so you can look at it. These are some post hoc claims, post hoc observations that you can make given an embedding. Okay. Similarly, you can do that for many other relationships, like you can say France minus Paris plus Rome is what. Okay, so you can predict that the resultant vector is very close to the vector representing Italy. Okay, so this is all good, and again, coming back to this question, which I will explain with a specific embedding called Word2Vec. Let's go to what are the use of embeddings for the next couple of minutes. Oh, we are already running out of time. So I'm going to talk about Word2Vec in the next lecture, where I'm going to give you a precise, I guess I'm going to give you an intuition of why such a classification task will produce vectors which are similar to each other if they are semantically similar. Okay, we have an example in the slide deck towards a few slides from now. But before that, let me discuss the use of embeddings. So if you look at the previous few minutes, I was talking about getting this W, right? So for each word, I want to get a vector, right? 300 cross 1, right? Or the W lookup table. But to get that, I said we'll create an auxiliary classification task, and we'll somehow learn W. Let's say we learned the W. What can you do with it, right? So these Ws are essentially representing unstructured data, right? In this case, the sentences, the document, the articles, and free sentences from your data source, right? So just like image embeddings, just like for images, the embeddings could be used as fixed feature extractors, right? In the fixed feature extractor setting, you could go from image to an embedding, and then from embedding, you can use it for any subsequent, a slightly different classification task and so on. Similarly, word embeddings, which were learned from sentences using that auxiliary classification task, which we don't care about. Once you learn these word embeddings, you can use them for any other task that you want. Okay, that's what people have seen empirically, that if you use them, you can do well. Okay, so we're seeing word embeddings, and once we learn W, this lookup table, you can use it for many tasks, and it's essentially an instance of transfer learning, just like we saw in the previous lecture. Okay, so here's an example. So you have words, and you get to this essentially the W lookup table. Then here C was a classification task. Okay, C was a classification task for which you learned. Then you can connect the same lookup table or the word embeddings and use it in a different task. Okay, which is what I've been saying. Now, there are a few key benefits of doing this word embedding. The first thing is you can train with more than one kind of data. So we learned W, let's say, using those sequences of 5 words, 5 words from, let's say, Wikipedia or New York Times or something like that. Then we can actually learn. So if we learn W, then we can learn a way to map multiple data into a single representation. So think of 2 different data sets, right? So let's say there's English words and there's Mandarin words. And actually, let's look at this example. So we have English words and have English word representation, word vectors, and we have Mandarin words and Mandarin word representations. Okay, let's say these both representations are in the same dimension. Let's say 300. Each word is basically 300 dimensional vector. Now, these vector spaces, these 300 dimensional vectors live in 300 dimensional vector space, but they may not be related to each other, right? So for example, English for university will be some vector, English, Chinese for for university will be some other vector. But if you know something about these two languages, let's say there are some pairs of words for which I know they're exactly, they are synonyms, sorry, not synonyms, they're translations of each other. If you already know that, then you can actually impose that constraint and ensure that these two word vectors align with each other. So for example, if you ensure that the university word vector and the university word vector in Chinese, they have exactly the same vectors, then, and you can do this from other words, then it can generalize to words which you did not know were semantically similar to each other. Okay. For example, um, let's say you train WEN and WZH, which are just English and Chinese word representations, then words that we did not know were translations can end up close to each other. Then you'll know that you'll know translation. So this is one way to do translation, machine translation, but quite naive and probably bad way. But so here's an example, like for example, business and this word, let's say we did not impose a priori that they were, semantically similar to each other. But if we train such that and with the constraint that the known words should have similar vectors, then we can get similar vectors for no words which you did not know before. And here's a 2D projection of these word vectors where the green words are Chinese and yellow words are English. And you can see the words, I mean, we can see the words that were imposed to be the same and the words that we did not know are closer to the words in English. So we can interpret that way. Okay. I think I really ran out of time. So this is an example of essentially a shared embedding, because two languages, two different words, symbols, two different sets of symbols are sharing the same vector space. Okay. Um, So with that, let me actually stop at this point. I realized we ran out of time. So next time we'll actually go to Word2Vec, and there I'll try to answer this question, key question. Why would, and Word2Vec will have its own classification task, and we'll see why would the words end up getting similar vectors if they appear in similar contexts. Okay. So we'll address that in next class. And with that, let's stop. If you have any questions, I'll stop the recording, but if you have questions, you can ask it in chat, or you can stay back for a couple of minutes and ask on chat or verbally. Thank you so much. Thank you so much.